All right, so let's solve some problems dealing with our Newton's laws stuff. So we can actually apply these to a couple more different examples and see how some of them work together. So we'll do one example here quickly, which will be a direct application of Newton's third law, right? So remember what Newton's third law is. For every force, there's another force that is equal in magnitude and opposite in direction. So basically just kind of dealing with when objects kind of interact with one another, they have to be applying these forces between each other, right? Again, if I lean up against the wall, I push against the wall has to be pushing back on me, right? Anytime these two things interact, there has to be some equal in magnitude and opposite in direction forces being experienced between them. Okay, so let's say we have three different boxes. We have a couple small ones and one medium-sized one. So we've got a couple different boxes here. We're going to say that this first one is 3 kilograms. So this middle one is 5 kilograms. And this last one here is 4 kilograms. And then what I'm going to do is I'm going to push on this. I'm going to apply a force of 20 newtons, right? I'm going to push with a force of 20 newtons. On the left side of here, I'm going to push all of these boxes to the right. And what I want to know is what force does the 5 kilogram box experience from the 3 kilogram box. So in other words, again, I'm going to sit here, I'm just going to push with a force of 20 newtons on all three of these boxes, right? I'm going to push on this 3 kilogram box, but then the 3 kilogram box is going to push on the 5 kilogram box. The 5 kilogram box pushes back on the 3, but then we all know we're going to be pushing this forward. So then there's also some sort of pair of forces between where the 4 kilogram box is pushing the 5 kilogram box backwards, and the 5 kilogram box is pushing the 4 kilogram box forwards, right? So these are all the different forces that we're going to have to try and kind of figure out and see what we need to do with. So the first thing that's going to be very helpful with this is let's just treat all three of these boxes as one object. So, and figure out what the overall acceleration is. And that will kind of help me figure out the motion of each of these boxes and thus what the different forces acting on them are. So we have this, right? We have a 20 Newton force is being applied to this 12 kilogram object, right? We have 3 plus 5 is 8 plus 4, 12 kilograms. So we have F equals ma. So we have 12 kilograms times a, the acceleration, right? So with this, we can just very simply solve for the acceleration of all of these boxes together, right? So this a is just going to be 20 divided by 12, 20 newtons divided by 12 kilograms, and this ends up with an acceleration of 1.67 meters per second squared, right? And so again, this acceleration will apply to all of them, right? They're all just kind of moving together as this one object. It is, three different boxes, but if I push on this one, they will all start to slide to the right and they will all experience this exact same acceleration. So now with this, we can start looking at the individual forces acting on these different boxes. So again, what we want though is we want the force that the 5 kilogram box experiences from the 3 kilogram box, right? So this 3 kilogram box is going to be pushed into it and this 5 kilogram box will experience some sort of force. So let's do our free body diagram for this 5 kilogram box and look at what all the different forces acting on this box are. So if we have my 5 kilogram box here, we have some force from the 3 kilogram box pushing it to the right, but then it runs into the 4 kilogram box and the 4 kilogram box. It'll push the 4 kilogram box and the 4 kilogram box will push back on it. So we have some force to the left from the 4 kilogram box as well. So with this, we can again do our Newton's second law just for the 5 kilogram box. And what we know is we have to have force from the 3 kilogram box plus the force from the 4 kilogram box has to be equal to ma of the 5 kilogram box. What's the mass? It's 5 kilograms, right? What's the a? We already know that it's 1.67 meters per second squared. So if we can figure out what this force is from the 4 kilogram box, we can then plug this in and we can solve for what the force from the 3 kilogram box is being exerted on this 5 kilogram box. So how can we figure out that one out? So the force from the 4 kilogram box is then going to be this. It's going to be, so if we look at just the 4 kilogram box, I can actually do the same picture, right? Just the 4 kilogram box, it only has the one force, right? It's just being pushed to the right by the 5 kilogram box. So the force from the 4 kilogram box is also just the net force acting on that box. And so we can say that this is equal to then 4 kilograms times 1.67 meters per second squared. So now this is the force that the 4 kilogram box is experiencing from the 5 kilogram box, right? It's just the one force being pushed on it. So this ends up being 6.67 newtons. But of course we know that in the case of the 4 kilogram box, it's pushing the 4 kilogram box to the right, so we can say that it's still positive. But when we go back to plug it in here, right, the force that the 5 kilogram box experiences from the 4 kilogram box is this same force, but to the left, right? The same strength, but in the opposite direction. So now we can write the force from box 3, right? Just go back and plug stuff in here, minus force from box 4, which we know is 6.67. This has got to be equal to our m times a, our 5 kilograms, times our 1.67 meters per second squared acceleration. So these are the two forces acting on box 5. This is the overall motion of box 5. This is the overall net force on the 5 kilogram box. So we can simply plug this in. We have the force from box 3 is equal to 5 kilograms times 1.67 meters per second squared plus 6.67 newtons. And this force ends up being exactly 15 newtons, right? So again, there's a lot to keep track of here. The overall math that we're doing, none of it got super complicated ever, but it's just a matter of understanding how we can apply our Newton's laws equations to the specific situation that we have, right? So we do have several different pairs of forces acting. We just pushed to the right on all of these boxes with a force of 20 newtons. There is some sort of force between here, right? We have a 15 Newton contact force between here. So the 3 kilogram box is pushing forward with 15 newtons on the 5. The 5 is pushing backward on the 3 kilogram box with 15. You can go back and you can do the math. You can see that the net force on this 3 kilogram box is then we have 20 going to the right. We have 15 pushing back to the left. So it's overall 5 newtons to the right is the net force on this box. You can do that and you'll see that you'll get the correct acceleration as well there. Then here we have another contact force of 6.67 newtons, right? The 4 kilogram box is being pushed forward with 6.67 newtons of force. The 5 kilogram box is being pushed backward with 6.67 newtons of force, right? Because again, Newton's third law, we have these third law pairs of forces between these boxes. So yeah, just a quick example there. Again, the math never gets super complicated. It's all the equations that I'm writing down here are fairly straightforward. We're just doing F equals ma over and over again. F net equals ma, I should say. But again, the tricky part is just kind of making sure we understand which equations we can write, right, and which ones are going to be useful and help us to try and solve this problem. So let's go ahead, let's do another example. This time we'll look at some friction. So let's say we are moving some boxes in our truck and we're trying to unload these boxes. So we have the box in the back of our truck, and we're going to try and slide this box down the bed of the truck, right? So we've raised up the bed of the truck like this. I guess our truck can do that, right? And we're going to try and do this. It's a very heavy box. We're going to try and raise this up to a certain angle, and we want to raise it right up until it starts sliding down the back of the truck, right? That's kind of the way that we're going to go about this. So we have some angle there, and what we know is the coefficient of static friction. I'll go over the difference between static and kinetic friction here in a second. The coefficient of static friction between the box and the truck, right, is going to be 0.8. And what I want to know is, when does the box start sliding? What angle does the box, oops, start to slide, right? So again, we have this ramp here that the box is on. We're going to increase the angle slowly over time, and then at some point the angle is going to be steep enough that our box is going to start sliding down this ramp, right? And what I want to know, I'm just giving you the coefficient of static friction between the box and the bed of the truck, between this box and the ramp. And what I want to know is at what angle does this box start to slide? First of all, let me go over a little bit. Again, what do we know about friction? Let's make sure we understand our force of friction in general is our coefficient of friction times the normal force, right? What materials do you have? How hard are you squeezing those materials together? That's the two main things that are going to determine how strong our force of friction is, right? So we know it's going to be friction holding this box in place. Let's go over the difference between static friction and kinetic. I've just written this. This can be either static friction or kinetic friction. The only difference between them is static friction means that your two surfaces that are in contact, right? We have the force of friction from the box between the bottom of the box and the ramp here that we have. Static friction just means that it is the force of static friction that is acting because the box has not started to move yet. Once this box starts actually sliding, it's a thing called kinetic friction. It works the exact same way, right? The way it works out, though, is that the force of kinetic friction after you've already started this box sliding down the ramp or anything sliding along any other surface. Once you've done that, once you switch over to kinetic friction, you just have a slightly different coefficient of friction, and it's always going to be a little bit less than the coefficient of static friction, right? So, sorry, excuse me. Okay, so yeah, so the only difference between static and kinetic friction, again, is whether or not the two materials are moving relative to one another. So again, when I have this notepad sitting here on this table, if it's sitting still and I try to push it, I apply some sort of force to the left or to the right and it doesn't move, it is static friction holding it in place. If I move it and I start moving it, now I'm still feeling some sort of force opposing my motion, right? It still works the same way that it's trying to oppose the motion of this book. But now once it is sliding, it is going to be kinetic friction, right? So static versus kinetic, they both function the same way. You just plug in a different coefficient, right? That's kind of essentially what's going on. And again, kinetic friction for any given set of materials will always be weaker than static friction. Again, that kind of makes sense. You kind of know this if you ever tried to, again, just move like a couch across the room. Maybe you push on it really hard at first. Once it gets going, it's a little bit easier to keep it going, again, because now you've kind of overcome that force of static friction, and you started sliding it, you now are working against kinetic friction to move this couch around, or in this case, to move this box around as it slides down this ramp. But again, our goal is to say, what angle does the box start to slide? What angle does it just initially start to slide at? So let's draw our free body diagram, and let's see what we can write about our with our Newton's second law equation, what we know about this. So let's go ahead. What are all of the forces on this box? We know gravity. It's going to be acting straight down. And again, I'm going to take this opportunity to point this out as well. The only piece of information I've given you is what the coefficient of friction is, right? I'm not telling you what the mass of the box is. I'm actually not even telling you what planet you're on, right? I'm not even going to specify that little g is 9.8. We're just going to say, with only knowing the coefficient of static friction, we can figure out when this box will slide. So we have our gravity pointing straight down. We have our normal force, which is, again, perpendicular to the surface that our box is on. We know that this angle here is also going to be this angle theta. Again, you can do your geometry review. You can kind of visualize it though as we tilt this up, right? As we kind of move it away, this angle here is being offset, but at the same amount that this vertical is from our kind of new vertical that we have here. But then, of course, we do have friction, which is going to go in this direction. So again, friction is always going to act parallel to the surface. So in this case, the only direction it can go would be up the ramp or down the ramp. But we know that our box is trying to slide down the ramp, and it is static friction that is pulling it back up the ramp and applying that force on it. So we have this case here. What we want to do is we want to try and max out this force of static friction. So the maximum amount of static friction that we can ever have is, again, right when this is going to be right when this force of static friction is balancing out the force of gravity trying to pull this down. So the angle that it starts to slide at is we're going to say that the acceleration of this box is still 0, but we're right on the edge, right? We're just barely balanced if this gets tilted up. If you walk past this, if you breathe on this box, it's going to overcome this force of static friction and push it down. But we're right exactly at the point. That's what we want to know. When the box starts to slide is when we're right at this kind of breaking point where the force of static friction has been maxed out and it's not able to be any stronger. So, and if we tilt this ramp up ever so slightly, or if we, blow on it, right? Blow on this box a little bit, applies just a teeny tiny slight force, we will start sliding down this ramp. So what does that give us? Let's sum up our forces in the x and y direction. So if I sum up my forces in the x direction, what do I get? So again, as we said before, when we had our person skiing down the mountain, you don't have to do this, but I think it makes it easier. Go ahead and tilt the coordinate system and that to put the direction of motion that, well, in this case, the box is not moving, right? But the box, if it were to move, it would be moving down this ramp, right? Go ahead and tilt this so that the direction of motion, right, is the overall net force that you would be experiencing if this box were to start to slide. You can just put that in one dimension. So we're going to have our x coordinate be, this is our x direction, this is our y direction. Our x is down the ramp, positive x is down the ramp, positive y is perpendicular up off the ramp is what we're going to use for our coordinate system. So in the x direction then, what do we have? We have gravity pulling in the positive x direction. Which component of gravity? It's got to be this right here. This is opposite that angle. So we would have mg times the sine of theta minus the force of friction equals what? Well, it's not actually moving. It's just about to be. We've just maxed out this force of static friction. So we have this, right? There actually is, we're just perfectly balanced. So we have 0 forces. Our overall net force is still going to be 0. So with this, again, we were trying to figure out this angle. At this point, we can't really solve for it yet. So let's see, let's look in the y direction, see what else we can figure out about this. So if I sum up my forces in the y direction, I get something that looks like this. We know we have the normal force is going up in the positive y direction, and we have minus mg times cosine of theta in the negative y direction. This is also going to be equal 0, right? Our box is not falling through the ramp. It's not bouncing off the ramp or anything like that. So what else again do we know about our force of friction? Our force of friction is again mu times the normal force. Well, with this force, with this equation where we wrote Newton's second law for the y direction, we now have an expression for the normal force, right? So of course, you can very easily see the normal force is just going to be equal to mg cos theta. So let's go ahead and let's plug that in for our force of friction and then what we know about our normal force. So we can say mg sine of theta minus mu times mg cosine of theta equals 0. So now simply solve for this theta, right? We know what mu is. We don't know m. We don't know g. That's okay. As it turns out, this m and g are going to cancel, right? The mass of the box doesn't matter. The planet you're on actually also doesn't matter. You can go to Mars. You can go to the moon. This box will start sliding at the same angle. So let's go ahead now. Let's just do our algebra. Let's solve for this. We have sine of theta equals, you add this over, mu cosine of theta. Mu equals sine divided by cosine tangent of theta. And so, of course, our theta is then the inverse tangent of the coefficient of friction. Remember, this is 0.8. We're given that, right? I told you the coefficient of static friction. I'm just using mu. Mu s is just static friction. If it's kinetic friction, you can abbreviate it mu k. It doesn't really matter. Just to make sure you know which one you're talking about. I'm never going to have you memorize coefficients of friction for various pairs of materials. You don't have to do that. You'll either be given it or you'll have enough information that you can solve for it. So you have this 0.8. Go ahead, plug this in here. And our angle that we get ends up being about 63 degrees. So yeah, as I said before, the mass of the box doesn't matter. The planet that you're on, right? The acceleration due to gravity actually also doesn't matter. Both the m and the g cancel out, right? When we go and we plug in for our, what we know has to be true for our force of friction, mu times the normal force, mg sine theta minus mu mg cosine theta equals 0, and you get this expression here. So if you take this truck and you take this box, you fly them out to the moon, and you start tilting the bed of this truck up, the box will slide at about a 63-degree angle every time, no matter where you are. Okay, let's look at one more example um, that will help you out for one of your homework problems. It's very similar to, I believe, number 5 on your homework. So let's see here. So we have the, um, this one is going to be something that we do called the Atwood machine. So the Atwood machine problem is what we're doing. So what is an Atwood machine? It is a very simple pulley system with a mass on either side. So here's our pulley. Here's some strings attached to either side of the pulley. And we have masses hanging off of either side. I'm going to call them M1 and M2. And the only thing I'm going to tell you is, I'm not going to put any numbers to this, I'm just going to say M1, whoops, M1 is greater than M2, right? So that's just kind of an arbitrary distinction. These are just labels, right? I'm just saying I have a mass here, I have a mass here. They are attached by a string that is wrapped around a pulley, right? So it's the same string on each, attached to each one. And so M1 is greater than M2. So when I let these go, what's going to happen is M2 is going to go up and M1 is going to go down, right? And so with this, what I want to know is, what is the acceleration of M1? So when I let this system go, right, we all know, again, we have our pulley system here. They're attached by the same string. They're going to start moving like this. And what I want to know is exactly how fast is M1 going to start falling towards the ground, right? It's not quite going to be falling, right? It's not quite in free fall because you have the tension of the string. But yeah, so this is what we want. We want to know what the acceleration of this first mass is. Okay, let's go ahead. Let's start applying our free body diagrams to these objects, and then also let's do some Newton's second law stuff. Okay, so if I just take this object here, what are all of the forces on each of these masses? Well, we have the tension from the string, right, which will move in the same, it'll be pulling up on mass 1. It's also pulling up on mass 2. But another thing that we can keep in mind is that this magnitude of the tension in each case is the same, right? The strength of the tension is the same, and in this case, the direction of the tension is the same. It's one string that's been being wrapped around, right? So we know that this tension force has to be the same. Again, you can think of it as just a bunch of little Newton's third laws on each individual particle of the string as you go around it, right? So if tension is pulling them both up, and then of course we have gravity pulling them both down. And that's it. They each have tension up and they each have gravity down. Let's go ahead. We actually only need to work in one dimension for this, right? All of these forces are either straight up or straight down. And so we don't have to worry about any two-dimensional stuff, but we do need to write our Newton's second law equation, our F net equals ma, for each of these masses individually. So what do we get if we do that? For mass 1, what we have is T, whoops, not T equals, let me try that again. We have T is pulling up, so we have T minus M1G equals M1A1, right? So we know that that has to be true. Tension's pulling up. I'm going to put up as positive. Gravity is pulling it down. So we have our net force here. These are two individual forces equal to my mass times acceleration. Again, this is just Newton's second law applied to the first mass. Let's do Newton's second law applied to the second mass. I get something that looks very similar. We have T minus M2G equals M2A2, right? Now, what's another piece of information that we can use to solve this, right? So we don't know what the tension is. We don't know what the accelerations are. So right now, those are kind of the things that we don't know, right? I'm going to go ahead and tell you we're on Earth. We'll have GV 9.8. I'm not really worried about the numbers again. I'm just saying that if you are given the masses, what are these going to accelerate at? How fast are they going to accelerate? So one other piece of information that we can say, though, is this. It's going to be very important. We won't be able to solve it if we don't look at the physical situation and know that this has to be true. A1 has to be equal to minus A2, right? We know that this has to be correct, and we know that this has to be correct again because they are going to accelerate, right? But M1 is going to go down, M2 is going to go up, right? but they're going to move together, right? They have to be moving together at the same rate. If M2 goes up really fast, M1's going to be going down really fast, right? We know they're connected by this string, so they're interacting with one another. You can kind of think of them as almost as one object, right? With each of the masses and then the string here. But they have to be moving in the same way, right? They're going to be moving at the same rate. They're just going to be moving in different directions. So this lets me now plug in. I'm just going to get rid of the A1 and A2 stuff. I'm just going to call them both A, right? I'm going to say that mass 1 goes down. I'm going to say that mass 2 goes up. So let's go ahead and rewrite our equations with this new piece of information. Again, we know that they have to have the same magnitude of acceleration. It's just they go in different directions. So I can write then this. I have t minus m1g equals m1 times minus a. So I'm just going to use a for both of them. This one's going to be to denote that mass 1 is going down. We have t minus m2g equals m2a, right? So this mass is going down, m1 is going down, m2 is going up, is what we're going to say with that. So now from here, we have two equations. We have two unknowns, right? We don't know t, we don't know a, but what we do want is we want a, right? So we can go ahead and solve for t, plug it back in to one of our equations, and then solve for a, right? Let's go ahead. Let's use our second equation. Let's say we know that t is then equal to m2a plus m2g, right? So here's our physics. The rest of it, we have two equations, we have two unknowns. So the rest of it is just doing math, right? So if you were to do something like this on a homework or a test, and you get to this point here, probably give you 3 out of 5, right? If you couldn't sort through the algebra after this, but if you got these two equations, right, and you made this connection here, that may even be a 4 out of 5, depending on what kind of mood I'm in when I'm grading. So yeah, so we have this. Let's go ahead. We have t, we know from the second equation. Move this m2g over. T must be m2a plus m2g. Plug that back into our first equation. So now we have m2a plus m2g minus m1g equals minus m1a. I'm just moving the minus sign out to the front there. Okay, so now with this, we have one equation, we have one unknown. Let's solve. Let's collect our a terms. So I'm going to move this one over here. I'm going to move these two over to the right side. So now what do I have? I have this. I have m1a plus m2a equals, move this over, this becomes positive. Move this over, this one becomes negative. m1g minus m2g. And so I have this. I can factor out a, m1 plus m2 equals, factor out the g, m1 minus m2 times g, solve for our a, and what we get is this, m1 minus m2 divided by m1 plus m2. So this is our final equation. It kind of looks maybe a little bit complicated, but it actually should make some sense if we kind of go through this and see what we have. We have the acceleration of our masses, right, on this Atwood machine, right, the magnitude of this acceleration. We know for the case of mass 1 is going to be going down, right, so if we plug everything in, we'll get a positive number, but we know mass 1 is going down, we know mass 2 is going up. But yeah, so we have masses on either end of this. We're going to say our acceleration is equal to the difference in masses. It's the ratio of the difference in masses, right? M1 minus M2 divided by the total mass. So if you have more total mass, these things move slower, right? And that should make sense. With a larger mass, right, you're going to get smaller accelerations. It is, though, proportional to the strength of gravity of the planet that you're on, right? So if we're on Mars or the Moon, it will be a little bit different than if we're on Earth, right? Just for a given set of masses, right? So that should also make sense. It is ultimately gravity that's kind of doing the work to move this system of masses. Let's look at what makes it stronger. This acceleration gets faster when we have a larger difference in the masses, right? But again, it's the ratio of the difference to the divided by the total mass that we have. So this should kind of make some intuitive sense that what happens if we put if M1 and M2 are equal, right? If you put equal mass on either side, well, now you just have your Pulley system being balanced, and as you would guess, you don't even have to do any math for it. If I put 5 kilograms over here, if I put 5 kilograms over here, they're going to sit there and they're going to be nice and balanced, right? Which is borne out by our equations, right? If we have the same mass for M1 and M2, M1 minus M2 is 0. M1 plus M2 can be whatever it wants. It doesn't matter. 0 times anything is 0. Our acceleration is 0. They don't go anywhere. We can look at more extreme cases, right? Let's say we have mass 1 is much, much larger than mass 2. Basically, let's just say that mass 2 is 0, right? Mass 1 can, 1 kilogram or whatever. Mass 2 is 0. Well, what have you done? Well, then you don't really have an Atwood machine, right? You don't really have this pulley system. If I put a mass here and I don't put any mass here, I don't have like some sort of Atwood pulley system going on or anything like that. Essentially what I'm doing is I'm just taking a mass and I'm dropping it, right? There's nothing else to balance it out. And so, of course, what do we get in that case? If mass 1 is much greater than M2 than mass 2, or if just mass 2 is 0, right? If you think about it that way, what you end up getting is you get this ratio. You have m1 minus 0 divided by m1 plus 0. M1's cancel out, and sure enough, your acceleration is just g. Your acceleration is just free fall, right? Again, as we said before, if I just don't put a mass on one side of this pulley system, and I'm not really taking advantage of anything that the pulley is doing, right, or anything like that, I'm just dropping a mass, right? So you can have accelerations range anywhere from 0, right, if you balance out your pulley system, to the acceleration due to gravity, right, if you just drop one of the masses, right, is essentially what we're saying here. And then, of course, you can have anything in between, right, but a greater difference in mass um, and less total mass, right, is kind of what gets us closer and closer to our free fall case. So again, this is even just a one-dimensional case, but this is actually similar to one of your homework problems. So make sure to keep that in mind. This will help you out when you go to do it. But yeah, we have a very simple setup. We have T going up and we have gravity going down on each of these. But again, make sure we know how our tension works. The direction can change, but the strength of the tension has to be the same in each case. That allows us to solve for the T, plug back in here, do our algebra, and come up with our expression for our acceleration, right? But again, we are just doing our Newton's second law stuff over and over again, right? Figure out what the forces are, add them up, set them equal to ma, right? The individual forces should be equal to mass times acceleration once we add them up. And from there, that lets us set up our equations and solve for our different quantities.